This is the second video on the topic stress, strain and Hooke's law. In this video, the topics covered are stress and strain, unit for stress and strain, tensile stress and strain, compressive stress and strain, rigid body, elastic body, plastic body, Hooke's law, and some related formulas. Now, stress and strain. This is a body of length L and the cross section area is here, which is rectangular, and a force P is applied here at the center, which can be seen here. This P is a pulling force. Pulling force means force is acting away from the point. So one force P is here, another equal and opposite force P is here. When these two forces are equal in magnitude, opposite in direction and collinear, the sigma Fx becomes 0. So the body will be under rest even under the action of forces. Now what is the effect of force on the body when the body is at rest? Now this is a section XX which is cut here, and if I take this left hand side of the section, that will look like something this, and this is a force P which is acting here. But due to this force, the body does not start moving in the negative X direction. It is at rest. So how it is at rest? Because at this cross section, internal resisting force is developed by the body, and it is developed throughout the section, and this total resisting force will be R, and it is equal to P and opposite in direction to P. So this body is at rest. Similarly, if I consider the right hand side of the section, then the internal resisting force here developed is in this direction. This is the internal resisting force, and this is the force P. So this internal resisting force which is developed per unit area is called as stress. So stress is equal to internal resisting force divided by the cross sectional area. So now internal resisting force is R divided by area is A. Now here P is equal to R, so I can write P replacing the R, and this sigma is the symbol for stress. So sigma is equal to P upon A. So stress is equal to P upon A. Now when this force is acting here, this is a pulling force, what happens is it stretches this bar length of the bar L in this direction, and there is slight increase in length which is shown by red, and this is the increase in length delta L. Now this increase in length or change in length to original length is strain. The definition of strain is change in dimension to the original dimension. In this case, it is change in length per original length. So strain is equal to delta L upon L, and this epsilon is the symbol for the strain. This is the symbol for the strain. Now what is the unit for stress and strain? Now sigma is equal to P upon A. This is the formula for stress. Here the P is a force which is in Newton and its area A is in meter square. Then the unit of stress will be Newton per meter square. This is the SI unit. But what happens many times, the area is measured in mm square because the area is very small. So the unit becomes Newton per mm square, and sometimes Newton per meter square so is taken as Pascal. 1 Newton per meter square is equal to 1 Pascal, where Pascal is name of the scientist. Now if the stress is in Newton per mm square, so 1 Newton per mm square will be 1 Newton divided by, now mm into mm is converted in meter into meter, so 1 mm is 1 into 10 raised to minus 3 meter, and then again for the second mm it is 1 into 10 raised to minus 3 meter. So this minus 3 and minus 3, if it is taken up, it becomes 10 raised to plus 6, and the unit will be now Newton per meter square. Now 10 raised to 6 we can replace it by mega, because 10 raised to 6 is mega. So 1 mega Newton per meter square. Now this Newton per meter square can be replaced by Pascal. So this becomes 1 megapascal. So what is important here to understand is 1 Newton per mm square is equal to 1 megapascal. Now sometimes the force P is taken in kilonewton and area in mm square, then the unit of stress sigma will be kilonewton per mm square. Now 1 kilonewton per mm square will be, now kilo is 10 raised to 3 and 1 Newton per mm square is 1 into 10 raised to 6. So this 10 raised to 6 and 3, it becomes 10 raised to 9 Newton per meter square. So this, by taking this 10 raised to 6, I have converted Newton per mm square into Newton per meter square. Now this 10 raised to 9 can be replaced by giga. 10 raised to 9 means giga. So it becomes 1 giga Newton per meter square. Now this Newton per meter square can be replaced as Pascal. So this becomes 1 gigapascal. So 1 kilonewton per meter square is 1 gigapascal. So what is important to remember is 1 Newton per mm square is 1 megapascal and 1 kilonewton per mm square is 1 gigapascal. Now the strain is delta L upon L. Now this delta L is also length and L is also length. So it is ratio of 2 lengths. So it has no unit. Now here we will learn tensile stress and strain. Now if both the forces are acting away from the point, then it is a pulling force or it is called as a tensile force. So, and here this force, this is again a rectangular cross section and this is the point of intersection of the diagonal, that is center of this rectangle. So the force P is acting here and it can be shown here, and this line which I have shown here is the axis. So both the forces P are acting along the axis. Now what happens is, when this force is applied, this is the original length, and due to this pulling force there will be increase in length from here to here, which is delta L. So now here the tensile stress will be sigma is equal to P upon A. This force is called P and this is the cross sectional area of the section A. So this P upon A is the tensile stress. It is acting along the axis. This is the axis which I have shown here by the green line. So sometimes this force is also called as axial stress. This is acting along the length. So sometimes it is also called as longitudinal stress. And now the strain which is developed here, that is the increase in length upon original length. So increase in length divided by the original length, that is delta L upon L, is the tensile strain in this case. So here to remember is P is a pulling force and it is acting along the axis of the rod, and this tensile or the pulling force, due to the pulling force the bar gets stretched and there is increase in length of the bar. This tensile stress and strain, we will be taking it positive while doing the calculations. Then let us try to understand what is a compressive stress and strain. Now if the bar, instead of pulling, if we apply a pushing force means the force is acting towards the point. Now both the forces are here pushing, they are again acting at the same point here. Cross sectional area is same A. Now this is the length of the bar from here to here. Now this push, due to this pushing force, now this is the length and this length reduces here and decrease in length is delta L. This is the original length L. Now here this stress which is developed within the bar due to the compressive force will be compressive stress, and this stress is again P upon A. Now this is also acting along the axis, so it can be called as axial stress. It is acting along the longitudinal axis, so it can also be called as longitudinal stress. Now the strain which is developed here is a compressive in nature. So what happens here? Here there is decrease in length. So the decrease in length upon original length, that is delta L upon L, will be called as strain. So here this is the original length which has been shown as L, and here there is decrease in length. So here the P is a pushing force and is acting along the axis of the rod, and this compressive force causes a contraction in the bar. So compressive stress and strain will be taken as negative. Now few more things we will learn here about stress and strain. The two effects may be identified when the force acts on a solid material and which remains stationary. So what is that two? So the material will be one exert an internal resisting force which is known as a state of stress. So stress is developed in the body, and the second is experience dimensional changes, but the dimensional changes are usually very small and they are not normally seen with the naked eye. Then the direct force, the force which are producing a tension or compression are called as direct forces, and this stress is given the name as direct stress, but often the word direct is omitted. So even though it is a direct stress, we call it only stress. Now here there is another figure. Here the force is shown as F. This is the cross-sectional area. Now this is a three-dimensional figure, and this is a rod where the cross-section is a circle, and this dotted line is a internal resisting force which is developed. Now this force is again a pulling force. So this is the length of the rod, and this X is this dotted line is showing the increase in length. So applied force is F, which was we took it as P. Cross-sectional area is L. Original length is cross-sectional area is A. Original length of the bar is L, and this X is equal to delta L, that is change in length produced by the applied force F or P. Now the forces which are acting on the body or a component or a bar are often referred as loads. So the load that a particular body can withstand will depend on the dimensions of the body as well as the material it is made from. So in particular, its cross-sectional area when it is subjected to direct forces. So for example, if the cross-sectional area is doubled, then the load that the component or the body can withstand will be doubled. So what is here important is intensity of loading or load per unit area. So here also stress is force upon area, that is P upon A, but the load which the material can resist, sometimes we feel that strength of a material is a force, but it is not a force, it is stress. Let us see how. For example, if a rectangular bar of dimension 5 mm breadth and 20 mm in depth supports a load of 4000 and we want to determine the stress in the bar, then sigma is equal to P upon A. So this is 5000 divided by the area 5 into 20, that is the dimension 5 into 20. So the stress will come 50 Newton per mm square. Now take a second example, a rectangular bar of dimension, now I am increasing it 10 mm and breadth and depth is 20 and it supports a load of 10,000 Newton. Now what is the stress? Now again it is P upon A, so this becomes 50. So what is here important is if I increase the area, here the area is 5 into 20, I made it doubled here, this becomes 200, this is 100 here, I have doubled the area. Then I can double the force from 5000, I have made it 10,000 and stress remains the same. So if the cross-sectional area is double, then the load that the body can withstand will be doubled for the same stress. So the stress carrying capacity of the body is strength. The material fails up at a particular stress. So if the load is coming is more, what I have to do is I have to increase the area so that the stress is within the permissible limit. So we have to control the stress produced in a body. Now let us come to strain. In addition to stress, in addition to controlling the stress produced in a component or a body to avoid the failure, the dimensional changes also acquire considerations. Hence, strain is also important. Now, what is strain? Strain is change in length upon original length, and it has no unit. Now, the strain also we have to limit, because sometimes it can happen that the body has excessive deformation or bending, which we cannot allow. Now, how we calculate the strain? Suppose a wire of 2 meter length extends by 0.25 mm when acted upon by a tensile force, and determine the strain in the wire. So the strain is delta L upon L. So the extends by 0.25 mm is the increase in length. So increase in length upon original length, this is 0.25. Now this 2 meter, the 0.25 is in mm, so this 2 meter must be converted into mm, that becomes 2000. So 0.25 divided by 2000 will be 1.25 into 10 raised to minus 4, and the force is tensile, so the elongation also will be, strain also will be taken as tensile. So while calculating the strain, we must remember that delta L and L must be in the same unit, both must be in meter or in mm. Now let us come to rigid body. What is a rigid body? A rigid body is a solid body in which the deformation is zero, so small that it can be neglected. The distance between any two given points on a rigid body remains constant in time regardless of external forces exerted on it. So there are 2 points which are important in a rigid body. First is, when a force is applied on a rigid body, there will be no change in shape or size of the rigid body. So now suppose this is a body which is kept here on a tabletop. So the weight of the body W will act downward, which is active force, and this table can give a reactive force R upward. Now suppose this body which is kept on the table is very small, say wooden cube. So due to this small force, this tabletop is not going to change in dimension. There is not going to be any bending or any reduction in thickness of this tabletop. So when a very small force is applied on this tabletop, nothing is going to happen, no dimensional change at all, and we can say that the strain is zero. And when the force is applied, even under the action of force, if the strain is zero, then we can say that this tabletop is a rigid body. Or if I say keep few chalks, say 3-4 chalks I am keeping on this table, so it is not going to happen that immediately the tabletop will get compressed and there is change in dimension. Or if I keep some pen or a notebook, nothing is going to happen to this tabletop. So I can say that this tabletop is a rigid body. But if I go on increasing the weight of the body here, say I have, suppose that this is a table and 2-3 people sit on this, then this tabletop will get slightly deflected and then it will lose its rigidity. So no body is perfectly rigid. We cannot say that any body is 100% rigid. The body is rigid only for the small forces when there is no deformation, the strain is zero. Then that body is called as a rigid body. But even this tabletop, if I go on increasing the forces, then it will start bending or it will start showing the cracks, so the rigidity is lost. The second point is, a body is regarded as a rigid body if the distance between any set of 2 points in it is always constant. Now let us see how this happens. This is what I have already said, that in reality no body is a perfectly rigid. When two equal and opposite forces applied to the body, there is always it is always deformed slightly. So but now let us see, say this is a body here and this is on the tabletop. Now for this body, if I apply a force in the positive x direction, say that this is a wooden cube and these are the 2 points which I am considering, and this is the distance between the 2 points. Now what happens? If I apply a force, this body will start moving in the x direction. This whole body will move. So, but these 2 points will have the same distance. That is not changed. So the distance between any 2 points on the body, if it remains constant, when this body is subjected to loads, then this body can be called as rigid body. So even if this cube is of a steel, and if I apply the force with the hand, so it is not going to happen that immediately this body will get deformed due to this force. This body can start sliding on the table. So then this body can be called as a rigid body. This is another example. So what is important is rigid body is which does not deform under the action of loads or the external forces, and for the rigid body the distance between any 2 points of the body remains constant when the body is subjected to loads. So this is basically rigid body, and any body is not 100% rigid. Now what is a elastic body? The property on account of which the body regains its original size and shape on the removal of external deforming force is called as an elastic body. For example, rubber band. Now this is the original size and shape of the rubber band. Now if I apply pulling for one force from here and one pulling force from here, and I stretch the rubber, then what happens? Its dimension changes. Its length is now increased and the cross section is decreased. The thickness of this rubber band has reduced. But if I release this force and remove from the hand, it will again come back to this original shape and size. So what happens? That the body regains its original size and shape on removal of the external deforming force. Then this body is called as elastic body. Same way, if you take a spring from the pen, if you compress it, it gets compressed, and as soon as you release the compressive force, the spring will come back to its original position. Or if you take a sponge and you compress it, its thickness will be reduced. But as soon as you release the forces, the sponge will come back to its original size and shape. So the elastic body is that body which regains its original size and shape on the removal of the deforming force. Now elasticity is ability of a body to return to its original size and shape when applied force is removed. So this is what is elastic body. Now here also no body is 100% elastic. Even this rubber band, I cannot say that it is perfectly elastic and 100% elastic. Why? Because if I go on increasing the pulling force and go on stretching, then at one point the rubber band will break. That means the elasticity is lost. So every body behaves as an elastic body only up to a certain limit. Now what is a plastic body? The property on account of which a body does not regain its original size and shape on removal of the applied force is called as plastic body. For example, wet clay packed. Now suppose this is a platform, say this is also a tabletop, and this is say a wet clay pat which is kept here, and I apply a force from the top, a compressive force. What will happen? This will get compressed. So there will be decrease in height and increase in length. Here I have shown this face vertical straight line, but it will bulge, it will be a curve here. Okay, and these 2 points, this is the distance between 2 points, that distance will change here, it will increase. So plastic body is a body which does not regain its original size and shape on removal of applied forces. So when you apply a force, it changes in its dimension, but if I remove the force, still it will not come back to its original size and shape, then that body is called plastic body. Plasticity is the ability of a body due to which it does not return to its original size and shape when the applied force is removed. So, this is a plastic body. Now, stress, strain, their symbols and their units. This is a table. Just the direct stress, the symbol is sigma. How you pronounce it? Sigma. And the unit is Newton per meter square or Newton per mm square. Direct strain is epsilon. Epsilon. This is the pronunciation. This is the symbol, and it has no unit. Young's modulus we are going to see just now, and this is the symbol E, and it has the same unit as stress, Newton per meter square or Newton per mm square. Now let us come to Hooke's law. Before we start with the Hooke's law, we have to understand what is the elastic limit. So this is a rod here, and I am applying a tensile force P here and P here. This is the original length, and this is a tensile force, so there is increase in length delta L due to the force P. Now if I increase this force P to say P1, then the stress will become sigma 1, corresponding stress. Corresponding strain will be epsilon 1, and corresponding increase in length will be delta L1. Then if I increase further to P2, this is sigma 2, this is epsilon 2, and increasing length delta L2. Then further I increase it to P3, then this will be sigma 3, strain will be epsilon 3, increase in length will be delta L3. And if I go on increasing, and a point comes which is a force PV, the strain is sigma V, stress is epsilon V, and increase in length is delta LV. Now what happens after this sigma V is achieved? If I further increase the force, then when I am applying P1, P2, P3, suppose now this force is here P3, and I release the force, then this bar will come back to its original length L. That is, this body behaves elastically. So initially when I am increasing P1, P2, P3, this body will behave elastically, and it will regain its original length if I remove the force, applied force, up to the point PV and the stress sigma V. But if I cross this stress sigma V and I further stretch the body, then what happens? After that, if I remove the force P here, the strain which is developed in the body is permanent. It enters the plastic zone, and it will not regain its original length after that. So what is here to understand is, if I go on increasing this P slowly, there is one point and one stress which is I am calling here sigma V. Up to that is the maximum stress up to which this body will behave elastically. If the stress is sigma V or less than that, and if I remove the force, this body will come to its original length, it will get its original size and shape. But if I cross this stress sigma V, and if I stress it more than sigma V, and after that if I release the force, then the deformation is permanent. Whatever is increase in the length of this bar, that is permanent. It will not regain its original size and shape. So this stress, this maximum stress up to which the body behaves elastically, is called as elastic limit. So the material's elastic limit, that is the maximum stress that can raise in a material before the onset of permanent deformation. And SI unit of it is, again it is a stress, so its unit is Pascal. Now let us come to Hooke's law. Hooke's law states that the strain of a material is proportional to applied stress within elastic limit of that material. So within the elastic limit, this stress and strain, they are proportional. In other words, in other simple words, Hooke's law states that within elastic limit of material, stress is proportional to strain. So this stress sigma is proportional to strain. If I remove the sign of proportionality, this sigma becomes sigma is equal to capital E into strain. Or if I write this E is equal to, if I write, then this capital E will be, this strain will go down here, so sigma upon strain, where this sigma is stress and this E, capital E, is called as modulus of elasticity, or it is known as Young's modulus, and its unit is Newton per mm square, same unit as stress. So an epsilon here is strain. So the modulus of elasticity, the basic definition of modulus of elasticity is stress upon strain. So this ratio of stress upon strain is modulus of elasticity, and sigma, the stress and the modulus of elasticity, both have same unit. Now here are some formulas. The basic formula of stress is sigma is equal to P upon A, or from Hooke's law we get sigma is equal to modulus of elasticity E into strain. These are the two formulas for the stress. Strain, the basic formula is delta L upon L. Modulus of elasticity, the basic formula is stress upon strain. Now this modulus of elasticity is equal to stress upon strain. Now if I substitute the value of strain as delta L upon L, then this will be sigma into L divided by delta L. Now here strain is in the denominator, so this L will come at the top and delta L will be divided by delta L. Now if I substitute the value of stress as P upon A in this formula, then it will be P into L divided by A into delta L. So P upon A is stress and delta L upon L is strain. So this becomes the formula for E. So E is equal to P into L divided by into bracket A into delta L. Now if I want the formula in terms of delta L, so I take delta L from here, it will come here at the top, and this E from which is here, this is the E. So E, I take it here on the right hand side. So what happens? Delta L will be equal to P into L divided by A into E. This formula delta L is equal to PL upon AE we will be using many times to calculate increase in length or decrease in length. So this delta L, then this modulus of elasticity E, which is stress upon strain, then this strain and this formula of stress. These are the formulas which will be using in calculating to solve the problems. Now here if again I substitute P upon A as sigma, then the formula becomes sigma is equal to L upon E. So this is, if I know the stress, I can directly substitute stress as sigma. So use this formula and calculate delta L. If I know the strain, then sigma upon E is the strain. In this formula, sigma upon E will give me strain. If I write strain is equal to, this E is come here, so sigma upon E will give me strain. So if I know the strain, then sigma upon E is a strain, so this will become delta L is equal to strain into L, or here you can see delta L is equal to strain is equal to delta L upon L. If I want delta L, so this L will come here, strain into L, so strain into L is delta L. So for delta L, if we know P and A, we will use this formula PL upon A. If we know the stress, we can use this formula sigma into delta L upon E, that will give me the change in length. And if I know the strain, then I can use this formula strain into the original length L, that will give me the delta L. So these are the formulas which we have to remember to solve the problems. So be a master, learn everything very carefully. Thank you.